Here are some more improper integrals. Of course, they're improper because their bounds contain either infinity or negative infinity or both. So first step is let's make sure that this function is defined for all values from 1 to infinity. It is. This function has a domain of all real numbers, so no worries there. So the only place where we have improperness is at this infinity right here. So we're going to let b approach infinity and evaluate the integral from 1 to b of this guy right here. Now, hopefully we remember from earlier in the chapter how to deal with something like this. This is kind of a nice one where this piece right here differentiates down to better and better things. X minus 1 differentiates down to 1, which differentiates down to 0. So if we integrate the other piece, which is e to the negative x, we'll get easy stuff. Just don't forget to alternate the signs. It goes to negative e to the negative x, and then goes back to positive e to the negative x. This is integration by parts using the tabular method. Don't forget the plus minus plus, and then we go diagonally, and we get x minus 1 times negative e to the negative x, negative e to the negative x times x minus 1. And then we also have minus 1 times e to the negative x, minus e to the negative x. We're going to evaluate that at b and at 1. And we'll subtract the 2. And then we're going to let b approach infinity. So I think that maybe factoring out a negative e to the negative x might make things a little bit easier, because we've got two terms in here. They both have negative e to the negative x. So I'll factor out that negative e to the negative x, and I'll be left with just an x minus 1 here. And then if I factored out all of this, I'm left with a plus 1. Oh, that's fun. Negative 1, positive 1 are gone. Like the noble gas, are gone. So we get, let's see, we get that right there, the limit, and we have just negative x times e to the negative x. So negative b times e to the negative b minus a negative 1 times e to the negative 1. All right. So this part right here is a constant. This is just 1 over e. This over here is a limit that we have to deal with, right? So we're going to rewrite this as the negative. I'll factor out the negative. The limit as b goes to infinity of b over 1, or b over e to the b. And then we've got this plus 1 over e. Okay? Now how do we evaluate this limit? Well, we notice that the limit as b approaches infinity of the numerator is infinity. And we notice that the limit as b approaches infinity of the denominator is also infinity. So that means, you guessed it, L'Hopital. So L'Hopital's rule says that we can evaluate this limit by differentiating the numerator and the denominator separately. Well, that simplifies the top and does absolutely nothing to the bottom. And we know that when b goes to infinity, e to the b goes to the infinity, and 1 over infinity is 0. So we have 0 plus 1 over e. So 1 over e is the value to which that improper integral converges. Alrighty. So a little bit of L'Hopital, a little bit of integration by parts. Got a lot of things going on in that one. That's fun. All right. On this one, this is actually one that we started the notes off with. This is one of those bell curve looking pictures. You can scroll back up to the top to see that if you want, or go back to the first video. We have to break this up into two different integrals. One is going to go from negative infinity to some number. And then we're going to add that same number to positive infinity of the same integral. All right. So any number will do. 0 is the easiest. All right. So we've got two different improper integrals. I'm just going to do this one, because if we scroll up and we take a look at this picture, or if we even just analytically ask the question, is this function even or odd? The answer is it's even. It's symmetric with respect to the y-axis. So the right half and the left half are exactly the same. So instead of doing two different improper integrals, I'm going to save myself a little bit of headache. And I am going to say this is equal to 2 times the integral from 0 to infinity of 1 over x squared plus 1 dx. That is perfectly acceptable. All right, so let's see. We can't plug in infinity, so we're going to use the limit as b approaches infinity of the antiderivative of 1 over x squared plus 1 is arctan of x. We'll evaluate that at b and at 0. So we've got 2 times the limit as b approaches infinity of the arctan of b minus the arctan of 0. Well, the arctan of 0 is just 0 because the tangent of 0 is 0, so that's irrelevant. So now we just have to figure out what does arctan approach as its argument approaches infinity. Well, if we think about the original tangent graph, you might recall it looks like this. I hope you recall that it looks like this. Y equals tangent of x. That's the portion of the graph that we invert. So our quadrant 1 graph looks like that, and our quadrant 4 part looks like that. This is y equals arctan of x. So asking what happens to the output as the input approaches infinity is the same thing as saying what happens to the input as the output approaches infinity. In other words, we're looking for the value of this vertical asymptote, the place where the tangent is undefined. Well, that's pi over 2, folks. That's x equals pi over 2 over here. This is y equals pi over 2 there. So this graph approaches pi over 2 as we go to the right. Fantastic. So that's kind of a fun little callback to pre-cal. So the limit as b approaches infinity of arctan of b is just pi over 2. We're going to go ahead and multiply that by 2 because we've got the left half and the right half of this bell curve looking thing, and our answer is the pleasingly simple pi. Alrighty, so I think we have enough time to do one more improper integral. This is, at first glance, not improper. We've got 0, we've got 1, but then if we take a look at the domain here, we can't let we can't take the tangent of pi over 2, right? And if x equals 1, then we get that undefined tangent of pi over 2. So this is definitely an improper integral because of the 1. So we're going to replace that 1 with a b, and we're going to take the limit as b approaches 1 from 0, so from the left. So that would be the proper way of dealing with this improper integral. And we have to take the antiderivative of this. Well, the antiderivative of the tangent, flip back to your little bag of tricks there and remember, oh yeah, the tangent integrates to the natural log of the absolute value of the cosine. Because the derivative of natural log is 1 over the argument, so the cosine goes on the bottom, and the derivative of cosine goes on the top. Oh, but wait a second. We've got that negative out front because the derivative of the cosine is negative sine. So we'll have a negative sine over cosine times that negative 1 will take us back to the tangent. I forget, does the argument ever change? What a silly question. Of course it doesn't, but don't forget to unchain rule this. The derivative of pi x over 2 is pi over 2. So we have to divide by pi over 2, which is multiplying by 2 over pi. Cool. So that's a little bit of u substitution in our head. And we can go ahead and evaluate that at b and at 0. I'll factor out the negative because I like to do that. And we end up with the natural log of the absolute value of the cosine of pi times b over 2. I'll factor out the negative, not just the negative, but also the constant 2 over pi. So I'll put negative 2 over pi out front. And that makes things even better. And then we'll subtract the natural log of the absolute value of the cosine of pi times 0 over 2. All right. Well, this is cosine of 0 is 1, natural log of 1 is 0, so this is 0, so that part doesn't matter. What happens when we let b approach 1? That is going to take us from 0 up to pi over 2. Cosine is approaching pi over 2 from 1, actually, or from 0, right? So we've got from 0 to pi over 2. If we're taking the cosine of these values, we're going to start at a cosine of 1. We're going to end up at a cosine of 0. So this part right here is approaching 0 from the right. Approaches 0 from the right. Okay? Because that's what cosine does when we go from cosine of 0 to cosine of pi over 2, right? So if the natural log of our argument, and our argument is approaching 0 from the right, then we've already talked about this before, the natural log approaches negative infinity as we go towards 0 from the right. So this is going to be a negative infinity minus 0, which is negative infinity, times a negative is going to be positive infinity. This is a divergent integral.